So now what I'm going to talk about is I'm going to talk about Green's functions with respect to it's basically just an extension of the variation of parameters. Okay, so Green's functions is basically a way of synopsizing variation of parameters for second order differential equations. You can't use these for higher order DEs, but you can use Green's functions for second order. Okay, so what I want you to recall, or we're going to write down right now, is that YP, my particular solution, is going to end up equaling negative y1 times the integral of from 0 to x. Okay, so it's going to be with regard to x, 0 to x of f of x, or f of t, excuse me, times y2 of t over the Wronskian with respect to t of y1, y2. Okay, now this move actually right here where we have 0 to x is going to end up being really important because y1 is already y1 of x. All right, that's already a function of x, right? And so we're going to make a very clear distinction between what's going on there with the thing outside of the integral and what's going on inside of the integral. Okay, plus y2 of x times the integral from 0 to x of f of t, y1 of t, over the Wronskian of y1, y2, okay? Now, what I'm going to do here is I'm actually going to go in and I'm going to pull everything into a single integral, okay? This is then going to equal the integral, and I'm just going to switch my order. I'm going to make it y2 of x, okay? Very important. So this is going to go from 0 to x, y2 of x, and so y2 of x is going to be a constant, okay? It's going to be a constant with regard to this integral, right? This integral is going to be in terms of t, it's going to be dt, right? And they evaluate it from 0 to x, so y2 of x is going to be constant, okay? y2 of x, and then this will be y1 of t, f of t, over the Wronskian of y1, y2, okay, minus, and this will be y1 of x, again, same deal, times y2 of t, f of t, all over the Wronskian of y1, y2, all dt, okay? Now I'm going to combine some like terms, and so this is going to end up giving me the integral from 0 to x of y2 of x, y1 of t, minus y1 of x, y2 of t, divided by the Wronskian of y1, y2. Ta-da! Done. We found it. That's it. Okay? We're going to rewrite this. All right? It'll be rewritten as 0 to x of k x t f of t dt with kx of t equaling, okay, this guy right here. Okay? y2 of x, y1 of t, minus y1 of x, y2 of t, divided by the Wronskian of y1, y2. So now that we have Green's function, let's actually take a look at an example. Okay, so I'm just going to that integral of k x of t, evaluated from 0x f of t dt, and k x of t is going to equal y1 of x, y2 of t, brings down k x of t is going to equal y1 of x, y2 of t, minus y2 of x, y1 of t, all over the Wronskian of y1, y2.
Let's use Green's function now to solve a differential equation. So we're going to solve y double prime plus 4y prime plus 4y equals 15e to the negative 2x ln of x. Okay? So first, we're going to solve ly equals 0. And what we get is we get that yc, our complementary part, is going to be c1 e to the negative 2x plus c2 e x e to the negative 2x. All right, so that's our complementary part. Now we're going to utilize that complementary part, right, with y1 equal to e to the negative 2x and y2 equal to xe to the negative 2x, all right, in order to utilize Green's functions. So first I'll find that Wronskian. The Wronskian of y1, y2 is going to equal e to the negative 2x, negative 2e to the negative 2x, okay, and then xe to the negative 2x, and e to the negative 2x minus 2x e to the negative 2x. And we'll find the determinant of that matrix, and that will end up equaling e to the negative 4x. And you can pause the video for a second and go find that. It should just take you a second, okay, or maybe more than a second, but not too much more. All right. Now what I'm going to do is I'm going to plug it into my kx of t. Okay. So this is now going to be, right, y1 of x is going to be e to the negative 2x. y2 of t is going to be te to the negative 2t. And then minus, and y2 of x is xe to the negative 2x. And y1 of t is going to be e to the negative 2t. And all of that's going to be divided by our Wronskian. So this is k. And our Wronskian is e to the negative 4t. So what that'll give me is that'll give me now e to the negative 2x, okay, times t e to the 2t minus x e to the 2t, okay, which we could just actually write as e to the negative 2x e to the 2t times t minus x. All right? Now we're going to take k and we're going to multiply it by f. Okay, that portion right there. So this is now going to be k times f of t, by the way, is going to equal e to the negative 2x times t minus x, right? And then I'm going to have e to the 2t right here, and then times, okay, 15 ln of x over e to the 2t. Excuse me, e to the ln of t over e to the 2t, right? Because f is going to be in terms of t. So this is then going to give me, okay, e to the negative 2x t times 15 ln of t minus x e to the negative 2x 15 ln of t. And in the next step, what I'm going to do is I'm just simply going to integrate. Okay? It looks a little bit of a mess, but it's actually not that much of one. So now here's our integral, but remember our integral is actually going to be with regard to 0 to x. So any of my functions of x are in fact going to actually be constants. So this is going to actually be 15e to the negative 2x times the integral of t ln of t dt minus 15x e to the negative 2x times the integral of natural log of t dt. Okay, and then I just need to go in and solve both of those, or actually take the integral of both of those. Notice 0 to x, 0 to x. 2, 1. This now, our yp, is thus going to equal 15e to the negative 2x times, and this will be 1/2 x squared ln of x minus x squared over 4 ln of x squared over 4 minus 15x e to the negative 2x times x ln of x minus x. Okay? And then if we simplify that, so our yp is then going to equal, this is going to be 15x squared e to the negative 2x minus, or e to the negative 2x ln of x, minus 15 over 4 x squared e to the 2x minus 15x squared e to the negative ln of x, okay, plus 15x e x squared e to the negative 2x. Okay, so what we see here is that these two guys are going to cancel. Okay, and these have like terms, so this is going to end up being 15 over 4. It should end up being, right, 15 minus 15 over 4, so that's 45 over 4, x squared e to the negative 2x, and that is yp. So y, our full equation, is going to equal c1 e to the negative 2x plus c2 x e to the negative 2x, x e to the negative 2x plus 45 over 4 squared, and that finishes the equation. Okay, and so that's how we utilize Green's functions. In some cases, Green's functions can be a lot easier to use, right? Okay, a lot more algebra, but a lot less calculus, right? And no linear algebra actually involved inside of these. Quick note though, Green's functions can only be used for second order differential equations, never for anything more, okay? Because it just doesn't work the same way. Okay, that completes the lecture.